Hi, today we're going to simulate a sour water stripper in HYSYS 8.8, and essentially a sour water stripper processes water that comes from sources such as hydrotreaters, reformers, hydrocrackers, and crude units, essentially in an oil refinery. So let us start with the components. So essentially what you're going to do here is to add the components that we're going to be using in our simulation. Sour water essentially contains hydrogen disulfide, some ammonia, and lots of water. Essentially, it is a very small percentage. More percent of water is essentially hydrogen disulfide or ammonia. H2S is actually hydrogen disulfide is actually what makes the water sour. Now we're going to give it an appropriate thermodynamic set of properties. Um, and let us enter the simulation mode now. So first of all, we will add the feed stream. The feed stream essentially consists of water. It's 98 mass percent water. Rest 0.5 mass percent is ammonia, while 0.7 mass percent is hydrogen disulfide. So we need to put all these properties in order for the material stream to be specified. As you will see in a few moments, the green light will turn on. So we put our mass fractions here. So essentially this stream is first going to enter into a heat exchanger and then into a stripper column, which is essentially a distillation column. We can see that our stream has been specified. Now we will proceed to add a heat exchanger, a shell and tube heat exchanger. And we will double click it to see the interactive menu that we have to fill. We also have to specify the pressure drops, which are in the parameter tab. These are essentially 10 psi for both shell and tube respectively. We will choose simple weighted model for our shell and tube heat exchanger. In the worksheet, we will give the stripper feed a temperature of 200 degree Fahrenheit. So this is the feed that will be entering into our distillation column. We now choose the distillation column from the column template and insert it into our flow sheet. We double click the distillation column to open the interactive menu. There are 8 stages. We will set the reflux configuration to full reflux. We now enter the inlet stream, which is stripper feed, of course. And respectively, we will specify the condenser, overhead vapor outlet, and bottom liquid outlet. We will also specify, essentially give names to the energy streams. And as we can see that we can now proceed to the next step of the interactive menu. We will choose a simple decision column, and this is where we add in the pressures. So the condenser pressure is 28.7 psi absolute, while the reboiler pressure is 32.7 psi absolute. psi absolute. You have to push on the space bar for this menu to open, or you can click on the unit change button. Simply press next and next again. This is an optional menu, you don't have to fill it up. Simply press done. But before that, you have to specify the reflux ratio, which is 10 in our case. We have a reflux ratio of 10. So as you can see, our column will not run at this moment, and this essentially means that we have to provide in more values for it to run. So we can see that there are these parameters that are active. We have to deactivate the overhead vapor rate. We can see in the bottom that the degree of freedom becomes 1 when we deactivate it. we have to add another specification, which is the component fraction. So the name is ammonia mass fraction, stage is reboiler, spec value is 0.00010. Component is ammonia. The component is ammonia, and we can see that the software automatically starts solving the distillation column. For now, don't worry about the solution. It will not solve, but later in the video you will see that it does solve. So it's essentially a few buttons. Don't worry about it. Um, Meanwhile, we're going to look into a case study of this simulation. So what we will do is to see the changes for a range of stripper feed temperature ranging from 180 degree Fahrenheit through 210 degree Fahrenheit in 5-degree increments. So essentially what we have here are a few dependent variables and one independent variable. Our stripper feed temperature is the independent variable. Rest of all the variables are dependent variables. You do not need to worry about this. HYSYS will sort out the dependent and independent variables for itself. For now, just watch the process and try to replicate it in your version of HYSYS if you have it running on your machine. As you can see, I'm adding the variables into the case study. So the first column is objects. The variables are related to these objects. For the column, you have to choose the following stages. Stage 2, 7 of the liquid net mass, and similarly, stage 2 and 7 with variables vapor net mass. Close this, and now you can see that all the variables have been sorted as being dependent, except for stripper feed temperature, of course, which I specified earlier. By the way, sorry for saying essentially so many times. This is essentially wrong. As you can see, I've just made a mistake. I will go and add stripper feed temperature again, which is our only independent variable. You cannot make a case study without an independent variable, just as you cannot make a graph without an independent variable. Now you can put in the temperatures and the delta, which is 5. The temperatures are 190 degrees Fahrenheit to 210 degree Fahrenheit. So it seems there is a problem. And now we go back to our PFT in order to correct it. So yes, the feed bottoms portion was missing. I corrected the name, and then now I can add this dependent variable too, which I missed the first time. You have to add this dependent variable too. It was missing because I did not name the distillation column properly. And by the way, the column that was not converging, you you should just try checking the active and non-active buttons that are located in the ribbon. As you can see, the case study is complete. You can now check the results, plots, and print them or whatever you want to do with them. Thank you for watching.